Hello, this is the video for the buffer overflow vulnerability lab. First of all, we need to define what's the buffer overflow. We all know that the buffer has a specific size, and the buffer overflow would mean that the user is writing more to the buffer than it can hold. And what happens to the extra stuff that we try to put on the buffer? It ends up overwriting adjacent memory locations, and in this lab, we will try to overwrite the return address to redirect to the shellcode. In this lab, we were given 3 programs in C. The first one is called Shellcode. This is a basic program in assembly language that just calls a shellcode when we execute it. The stack C is the second program that we're giving in the lab. This will include the vulnerable buffer with 24 slots, but we are trying to input 517 characters to a 24 character buffer, so we're almost inputting 500 bytes to overwrite adjacent memory, and we're getting these 517 characters from the bat file that we generate in the next program. This is the third program that we're giving in the lab, exploit.c. In this program, we can see this is the code to execute the shellcode. This is here we generate the bat file, the 517 characters. We initialize the buffer with NOP instructions, and we replace 4 specific bytes of the buffer, and I will tell you in a minute why these specific bytes and to this specific address. Here I'm just inputting the shellcode to the end of the buffer, and this is just saving the contents of everything to the bat file. Okay, let's start with task 1. Task 1 is just running the shellcode. So we're going to compile the code, the call shellcode.c. We're going to use the executable stack option. Here it is. And then we run it. And there it is. Although this is not in root form, and we are aiming to create the shellcode but in root form. After that, we are going to compile the stack.c file, but before that we need to make sure to turn off the address space randomization. And there is. We disable the address space randomization, then we can compile our program. We make sure to execute it like this to turn off stack guard and making the code executable from the stack. Then we use the channel mod 4755 to allow the launch of a shellcode in root mode. Then we need to take a quick look to exploit.c, because these 4 bytes that are overwritten here are gonna be important, and I'm gonna explain why did I choose these specific 4 bytes. Then, as I said before, our goal here in the buffer overflow is to know the return address so we can redirect it to the NOP instructions or directly to the shellcode. And that's what we're going to try to find out in this part of the video. So we are going to disassemble the program using GDB to know where's the return address located, so we can override it with our own code. Then using the GDB, quiet command stack, and then with this symbol buffer overflow function. This is the binary code for the buffer overflow function that is located right here in stack.c. This is the function that we are looking at. We need to create a breakpoint right about here, because that's where the fresh base pointer is calculated, and we need that address to locate the return address. And we run the program, and then we check for the base pointer address, and we got the base pointer address. It's this one right here. Examining this code right at this line over here, we get this -0x20. That's the address for the base pointer, and the -0x20 in decimal is -32. So we know that the starting address for the buffer, it's 32 bytes before the base pointer. So if we know the address for the base pointer, we know the return address is 4 bytes after the base pointer, so it will be 36. So that's why right here on exploit C, this is overwriting those bytes, the ones from the return address, to this specific address. And I choose this address specifically because here, this is the address for the base pointer, right? So if we use that address, we will get nothing at all. We will just be redirected to the same place and nothing will happen. So instead of using this, I just tried, like, not guess it, but just count a little bit over the base pointer to try to get not at the exactly start of the shellcode, but in the middle of it, in the middle of the function and the buffer, to land right into the NOP instructions. We know that the NOP instructions are just instructions that keep executing one after the other until it gets to a code. So if we get to the NOP instructions, that it's this address over here, the BF FF EB B9, that's the address that I used. There, it's just right after this address. I got to make the program work, landing in the NOP instructions. So right now I'm going to compile the exploit.c file, and then execute it to create the bat file, and then execute stack file, and it should be over here our shellcode in root mode, and there is. We can use the id command to see that we are indeed in root form. So in task 3, we're going to add some code to the exploit.c so we can bypass the dash countermeasure implemented in Ubuntu 16.04. Because you can see right here the UID is still the same, the seed one, not the root. So to do that, we just comment this, save it, and then we compile it again, use the exploit and stack, we check it again, the EID, and it should be the root 0. And for task 4, we are going to try to defeat the address randomization. So we're going to use this command to enable again the address randomization. We're going to compile stack.c again. channel mode. We exit it. And then with the script that is provided on the lab, we're going to be executing the code over and over again, trying to use the brute force to get into a code and get to the root shell. And here we can see that after 53 seconds and 46,000 times that the script was running, we were able to get to the root mode. So yeah, address randomization is not a really good countermeasure for the stack overflow. And after that, for task 5, we're going to turn on the stack guard protection on the program. But first we need to disable the address randomization again. 0. And then we need to compile stack.c without the no stack protector command. Use the channel mode. Exit. And then after that we need to compile again or exploit to run it. And then run our stack. And here it says stack smashing detected, stack terminated, because the stat guard, what it does, it puts a random integer before the return address, and we're trying to overpass that address. We're trying to overwrite the return address. So in that process, we overwrite also the random integer that the stack put it there, so it can check that it's the same value, but we overwrite it, so the stack check the integer and it's not the same, so it detects that someone is trying to insert malicious code on the stack, and it instantly terminated the code. And that was everything for task 5. And for task 6, we need to turn on the not executable stack protection. So I'm going to go into root. I'm going to compile the file again, but instead of what I was doing before, the no stack protection is included again, and the no executable stack, it's now on the commands for compiling the program. We need to do the channel mode again, and we can exit. And now we need to try to compile our exploit file again and try to use the stack program. And it says segmentation fault, because the no executable stack does not let anything on the stack be executed. So the shellcode, even though it is on the stack and it maybe it was trying to execute this countermeasure, efficiently negate to do that. So my conclusions for this lab are the following. I was able to launch a root shell via buffer overflow vulnerability with the stack.c program. I used the debugger for finding out the address of the return address, so I can use it to redirect the code to the shellcode. And I also use the debugger for roughly knowing where is my stack located, how far is it from the base pointer, and that's how I know the bytes that I needed to use. And for the countermeasures, the address space layout randomization, I would say that it is pretty weak, because I was able to overpass it by brute force. Just the script took 50 seconds to crack the code and to be able to launch the root shell. And for me, the stack guard and the non-executable stack were effective against the buffer overflow, but I would say that the stack guard is better because the non-executable stack, maybe it will cause some problems if the function returns a call to another function. I don't know, it may be difficult to handle with that. So for me, the stack guard countermeasure was the best one against the buffer overflow. Thank you.